Hi class, welcome to your lecture on the normal probability distribution. This is an incredibly important lecture as some of the theories or processes that we talk about in this section are going to get expanded and talked about in future sections to come. I highly encourage you guys to take notes during this video as well as watch my second video that I'll post that includes just a bunch of examples on using the normal probability distribution, as well as all the optional videos that I have posted in this section, just because this will be an alternative way to see some of the theories, and the more you see different approaches from it, the more it might make sense. Okay, so today in this lecture I want to talk about the properties of the normal distribution and how we can use those properties in some type of application problem. All right, so here are the objectives we're going to get out of this lecture. Believe it or not, we're not actually going to start talking about the normal probability distribution. We'll talk about something called the uniform probability distribution, and this is just to give us an idea of how some of the properties that the normal distribution curve have are relatable to an example. And it's also sometimes easier to understand these properties when you look at something a little bit easier, such as the uniform probability distribution. All right, anyways, we'll graph the normal curve, we'll state the properties of the normal curve, and then we'll explain the role of area. All right. Area is going to come up a lot, and what's called the normal density function, or NDF. Okay, so first off, we're going to talk about how you use the uniform probability distribution. All right, and it's going to be this lengthy example, and I'll try to explain it as best I can. All right, so suppose that the United Parcel Service, so that's the UPS, is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 a.m. and 11 a.m. Okay, so imagine you're getting a package, and they call and say, hey, your package is going to be there between 10 a.m. and 11 a.m. All right, so let's let this random variable x represent the time from 10 a.m., okay, when the delivery is supposed to take place. All right, so the delivery could happen at exactly 10 a.m. Well, that would be x is equal to 0, because if we let x be the time from 10 a.m., all right, if it happens right at 10 a.m., the time was 0. Or, all right, at, let's say, 11 a.m., at the other extreme, well, then x would equal 60. All right, because you've had to wait 60 minutes. All right, so then we'll have all the 1-minute intervals of time between x is equal to 0 and x equal to 60 be just as likely. What that means is it's just as likely for your package to come or arrive between 10:15 and 10:16, all right, as it is to arrive between 10:40 and 10:41. All right, or another way, it's just as likely to arrive between 10:01 and 10:02 as it is between 10:02 and 10:03. Right? Just as likely. Okay. The random variable can be any value in the interval from 0 to 60. So x ranges between 0 at the low end, it arrived right at 10 a.m., all the way to 60, it arrived at 11 a.m. All right. Because any two intervals of equal length between 0 and 60 are inclusive, are equally likely, the random variable is said to follow what's called a uniform probability distribution. All right. What that means is because all the odds are the same, exact same, all right, it's uniform. Okay, so we have now what's called a probability density function, or PDF. And this is just an equation used to compute probabilities of continuous random variables. All right, like the time example, that's a continuous random variable. And we actually won't use the equations too much. We'll use different methods such as statistical tables or some intuition, especially with the uniform one, a little bit later. All right, it must satisfy the following properties. When you graph the equation, the total area under the graph of the equation over all possible values of the random variable must be 1. Okay, and the reason it must be 1 is because 1 represents 100%. So we're actually going to use area here to be some type of proportions, all right, or probabilities. Interesting. All right, the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. And the reason that is, if you think about what I just said, how we're going to relate it to proportions and probabilities, you can't have negative probabilities or proportions. Okay. All right, so here's what we want to do. The graph below illustrates the properties of that time example. Okay. So if you look here, we have this, this rectangle. Along the x-axis is the random variable, and there's 60 of them, right? Because if the package arrives 1 minute late, 2 minutes, 3 minutes, 4 minutes, all the way up to 60 minutes later than 10 a.m. or 11 a.m. All right. The reason I have the height up here be 1 over 60 is I want the area under this of this graph here to be 1. Well, if there's 60 random variables here, we know that the area of a rectangle is length times width. Well, 60 times 1 over 60 is 1. Okay. So this right here is our uniform density function. All right, and a lot of you might look at it and just say, well, that's just a rectangle. We're actually going to use it for something. All right. So we notice that values of the random variable x less than 0 or greater than 60 are impossible. All right. Thus that the function value must be 0 for x less than 0 or greater than 60. What I mean by that is the function, the graph doesn't exist for negative values or for anything greater than 60. Because x represents, when it's 0 is 10 a.m., and when x is 60, it represents 11 a.m. And that's what UPS said. Your package is going to arrive between 10 and 11 a.m. All right, so this is important. The area under the graph of a density function over an interval represents the probability of observing a value of that random variable in that interval. So a lot of times when you read that, it's kind of like, huh, what does that mean? Well, let me show you. So let's say you take the probability of choosing a time that is between 15 and 30 minutes after the hour, all right? The area under this curve between those two values is the probability the package will come between them. All right, so another way that this is asking is say, well, what is the probability that the package will arrive between 10:15 and 10:30? Well, if you calculate that area, all right, well, length, so to go from 15 to 30, all right, that's 15. Length times 1 over 60, all right, so 15, it ends up being 50 times 1 over 60, which is 15 divided by 60, is 0.25, or 25%. So there's a 25% chance that the package will come between 10:15 and 11:30. All right? That area gives us that probability. So the probability that the package is between 15 and 30 minutes after the hour is 0.25. And what we get from this is the area under the curve here gives us that probability. All right, so now hopefully we kind of have some understanding that we're going to use area under the curve for probability. All right, now we're going to talk about how this all relates to a normal curve. All right, so the first thing we want to talk about is how you graph a normal curve. All right, so the relative frequency histograms that are systematic and bell-shaped. All right, so if you just ignore the red, yellow line on top here, but just look at this histogram, all right, are said to have the shape of a normal curve. So if you look at this, just the histogram, it looks very much like a bell curve. And if we impose it or superimpose on it this bell curve shape here, you can see that normal curve. All right? And we actually talked about normal curves way back during our second lecture of class when we talked about what type of shapes histograms can have. All right, so this is something that you should have seen before, actually. All right. If a continuous random variable is normally distributed or has a normal probability distribution function, then a relative frequency histogram of the random variable has the shape of a normal curve. All right? That means it's bell-shaped and symmetric. All right, what I have here is just a kind of a graph of it, and I want to go over some key features of it. So first off, the highest point of the graph up here occurs at mu. So whatever the average is of the random variable, whatever the average is, that's right smack in the middle at the highest point of the graph. If you look at this point, that's the average plus 1 standard deviation and the average minus 1 standard deviation. This point and this point are the exact same points of the graph. Right? So they're just like inflections of each other. So what I mean by that, if I were to cut this graph in half and fold it over on top of each other, they would fall perfectly right on top of each other. And it doesn't just happen at this point and this point, but every point. So here has an inflection point over here. Here has one over here, and so on. All right, I just want to show you what different normal curves look like. So this one is mu equals 0, so it's centered at 0, and it has a standard deviation of 1, and it looks like this red one. This standard normal curve has a mean of 3, so it's centered at 3, and a standard deviation of 1. So they look exactly like each other, all right? Just one is centered at 0 right here, as you can see, and the other one is centered at 3. All right, if you look at these two here, all right, they both are centered at 0, so they're both, for the data sets or whatever, have an average of 0. But this top one has a standard deviation of 1. This bottom one has a standard deviation of 2. All right, so what this illustrates here, if you have the same average, a larger standard deviation down here means the data is a little bit more spread out. So it's shorter and fatter, if that helps to see it. Smaller standard deviation, taller and skinnier. Okay. So let's state some of the properties of the normal curve. All right. First one, it's symmetric about its mean. All right. So that means it's perfectly centered at its average. All right. Because, this is important, the mean is equal to the median equals to the mode. All right. They're all the same for a normal curve. The curve has a single peak at its highest point, which occurs, the x value of that is at the mean. So if I go back to this right here, forgive me, the highest point of each of these graphs occurred at whatever I said the mean was. Mean is 0. Highest point. Mean is 0. Highest point. Okay. Has inflection points at mu minus sigma and mu plus sigma. All right. Area under the curve is 1. All right. That's how we're going to relate it to probability. All right. And the area under the curve to the right of mu is the same thing as the area to the curve to the left of mu, which is 1/2. All right. So what that means is that half the area falls above the mean, half the area falls below the mean. So if you look at this red curve here, half of the area is above, half is below. All right. Next thing, as x increases without bounds, so as x gets larger and larger and larger, all right, the graph approaches but never reaches the horizontal axis. All right, and it's the same thing as x decreases without bound. All right, that means x gets more and more negative. It approaches the horizontal axis, but it gets so close to it. All right, and the empirical rule, which we learned a while ago, holds. All right, so approximately 68% of the area under the normal curve is between the mean minus an average and mean plus the average. Approximately 95% of the area is between the mean minus 2 standard deviations and the mean plus 2. And then if you take it out to a third standard deviation like we learned, it's 99.7%. All right, so here's a visual of that. So if you just look right here in this kind of turquoise color, within 1 standard deviation of the mean on each side, all right, it's 68%. And additionally, because it's symmetric, that means between the mean down 1 standard deviation is 34 and the mean plus a standard deviation is 34. All right, it's not implicitly written on here, but between from this point right here to this point right here, it's 95%. All right? That means 95, if you take that divided by half, is 47.5. So if you take 34 plus this 13.5, that gets you that 47.5%. And you can do the same to get the other numbers. Additionally, I'm going to do another video that shows you how to work values from this table right here, or from this graphic right here. So when you go to watch the next video, please print this out and have it handy, and I'll show you how to use it. Okay. Next thing I want to do, I want to explain the role of area in the normal density function, right, for the normal distribution. All right. So I'm going to have data on the next slide represent the heights in inches of a random sample of 52-year-old males, so some young kids. All right. So I want to do two things. I want to draw a histogram of the data using the lower class limit of the first class equals to 31.5 and a class width of 1. All right, and then I'm going to say, do you think that the variable height of a 2-year-old male is normally distributed? All right, so here's the data. So just like what we've done with histograms, what I want to do is I want to take this data and I want to summarize it into a nice table, a nice frequency table. Then I want to do a relative frequency from it, and I want to look at the relative frequency histogram. All right, so I do that for you. And this is what our relative frequency histogram looks like. So each class width here, all right, as I put over here, is 1 inch. All right. So if you look at this histogram here, all right, ask yourself, what does it look like? And to me, it looks like that normal bell curve. It really does. It's not perfect, but it looks a lot like it. All right. So here's what happens. In the next slide, we have a normal density curve drawn over the histogram. So I'm going to draw that normal bell curve. All right. And then here's a question I want you to ask yourself. How does the area of the rectangle correspond to the height between 34.5 and 35.5 inches relate to the area under the curve between those two values? Okay, I'll explain that. All right, so I drew on top of the histogram, a normal bell curve, normal distribution. All right, So I want us to look at the height, or excuse me, the area of the rectangle between 34.5 and 35.5. So this rectangle right here, and compare it to the area under the curve between that. So from here to here, that area. Well, if I highlight it, this green area right here looks almost exactly like the area underneath the curve. Like if you look here, if I were to continue that curve and fold that over and put it here, all right, it might be just a little bit more. But what I'm getting at here is that this curve, all right, the area under the curve is a good approximation for the area of that rectangle. It's a great approximation, actually. All right, so now what we could do is talk about area under the normal curve. So we're going to talk about how we use area under the normal curve to approximate this area right here. All right, so suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. All right, so and for all these examples, I'll give you the mean and I'll give you the standard deviation. The area under the normal curve for any interval represents the values of the random variable represent either the proportion of the population with the characteristic described by that interval of values, or the probability that a randomly selected individual from that population will have the characteristics described by the interval of values. All right, like what the heck does that mean? I promise you I'll give you a good example to make this, have this make sense. All right, and we won't use the height of males ones, we'll do a different one. And it might seem a little silly, but suppose the weights of giraffes are approximately normally distributed, with on average giraffes weigh 2,200 pounds, that's a lot, and they have a standard deviation of 200 pounds. Okay, so here's what I want to do. A, I want to draw a normal curve with the parameters labeled, and you'll see that. What I mean by that is I want to draw the normal curve and count off standard deviations. All right, I want to shade the area under the normal curve to the left of x is equal to 2,100 pounds. And suppose that the area under the normal curve to the left of what I shaded, okay, to the left of x is equal to 2,100 pounds is 0.3085. And I want to provide two interpretations of that result. Okay, so here's the first thing I did. I'm going to draw a normal curve, all right, and I'm going to shade in the area under the normal curve to the left, 2,100 pounds. All right, well, here's a normal curve. You'll notice that the highest point of the normal curve right here occurs at 2,200 pounds. All right, and then what I started doing is I started labeling just every 100 value, every 100 pounds. All right, so 2,100 pounds is a little bit below the average, so I would draw a line up to the top of the normal curve, and then I would shade in everything to the left. All right, so this normal curve right here represents the distribution of giraffe weights. And I think that makes sense, right? If the average giraffe weight is 2,200 pounds, there'll be some giraffes who weigh a lot more, but not as many. And there'll be some giraffes who weigh a lot less, but not as many. Okay, so what does this shaded area represent? So here's what I told you. I told you that the area under the normal curve to the left of 2,100 pounds, this blue shaded area here, is 0.3085. Okay, so what does that exactly mean? All right, here's two interpretations of it. You could say then that the proportion of giraffes whose weight is less than 2,100 pounds, so all the giraffes that are out there, the proportion that weigh less than 2,100 pounds is 0.3085. Okay? So another way to say that is 30.85% of giraffes weigh less than 2,100 pounds. All right? Or if we were to just randomly select a giraffe at random from the wild, just go out, grab that giraffe. Right? The probability that that giraffe weighs less than 2,100 pounds, it's the same thing. All right. So that's incredibly powerful to say. We're using this normal curve to approximate either a proportion, to say something about a proportion of all giraffes, or to say something about the probability of randomly selecting a giraffe and having that characteristic. All right, I promise you that this will continue to make more sense after the next video and then during our lecture in class. All right, thanks for listening, guys.